All right, for this video, we're going to look at 1.4's example problems. If you'd like to see the theorems and the definitions and whatnot, you can go to my website and look at the PDF of the lesson, or you can look at your book, and those will be basically the same thing. So we're just looking at 1.4's example problems, continuity and one-sided limits. All right, so first I've got three examples of functions that are not continuous. First, function is not continuous because I have a hole in the graph. All right, f of c is not defined. All right, there's no point there. Next one, the limit doesn't exist. As I approach from the left and the right, I am not approaching the same number, so limit does not exist. And the last one, f of c is defined, but it doesn't match the limit. And so these are three conditions of continuity, and each one of them must be filled in order to be continuous. So with that, let's look at the example problems. First, A, f of x is equal to 1 over x. I can look at the graph of this and tell that at x is equal to 0, I've got a vertical asymptote. You can also tell from the function I can't divide by 0. So I am not continuous at x is equal to 0. It is continuous on all other numbers. So I am going to say for A, we are continuous on negative infinity to 0, and then 0 to infinity. All right, for part B, get the graph of that. We are discontinuous at x is equal to 1. This is a removable discontinuity. I can plug that hole, but it's still not continuous. If you plug this into your graphing calculator, it may look continuous to you because the calculator is looking at all values, and that one point, x equals 1, looks filled in, but it's not. If you look at the table, you'll see an error. All right, so this is discontinuous at 1. So we have our continuity, negative infinity to 1, and then 1 to infinity. So this is continuous on negative infinity to 1 and 1 to infinity. All right, let's look at the third example. The third example, I have a piecewise function, and both of the pieces are continuous for all real numbers. So what I need to check is if they match at x is equal to 0. So I'm going to plug in 0 for x, and I get 1, and plug in 0 for x squared plus 1, and I'll also get 1. And so they do match, and the graph looks like this, and I'm going to be continuous from negative infinity to infinity. I can also write continuous on all real numbers. Next, I want to find the limit of f of x is equal to root 4 minus x squared as x approaches negative 2 from the right. We just learned this. We've got the limit as x is approaching negative 2 from the right. I'm going to have a plus there. The plus means we're approaching from the right. If I have a negative sign behind the 2, that means we're approaching from the left of the square root of 4 minus x squared. Now, because I'm approaching negative 2 from the right, I need to make sure that this function is defined on the right of negative 2. I know it's defined at negative 2. I can plug that in and solve. It would be 0. But then if I plug in a negative 1, which is to the right of negative 2, I need to check. And this one would be defined at negative 1. If this problem read, as x approaches negative 2 from the left, I would then have to test values like negative 3, and I would end up with a negative inside the radical, which would be imaginary. So for this, it is defined on the right, and so now I am going to just plug in that negative 2, and I have 4 minus negative 2 squared, and 4 minus 4, root 0, which is 0, and that will be my limit. Next, the greatest integer function. The greatest integer function, it means the greatest integer that isn't bigger than the value given. So, for example, if I had the greatest integer of 2.9, the greatest integer not greater than 2.9 is 2. If I had negative 2.9, the greatest integer not greater than negative 2.9 is going to be negative 3. It's just going to be dropping down. So when I'm looking at this problem, I'm going to be evaluating the limit as x approaches 0 of the greatest integer of x. Now the graph of this is a step function. So here I've got a closed circle and I'm going this way. I'm going to have an open circle at 1. And then I jump up to 1 here and I continue, and it's going to look like a staircase. And then down here I'm going to have an open circle here at -1 and then a closed circle. So as I approach from the left, I'm approaching -1, and as I approach from the right, I'm approaching 0. So here, this is limit as x approaches 0 from the left of the step function. That's going to equal -1, and the limit as x approaches 0 from the right of the step function, that's going to equal 0. And so the limit does not exist if I were just to say the limit as x approaches 0 of the step function of x, because these two do not agree. Now we're supposed to discuss the continuity of f of x is equal to the root of 1 minus x squared. If you look at the graph of this, I'm going to have values here. It's going to look like this. And there's 1, there's -1. All right, so the continuity of this graph is going to be from -1 to 1. And the way our book defines it, it is continuous on those endpoints. Okay, so it will include those endpoints. Next, describe the intervals on which each function is continuous. Tangent of x is not continuous when cosine is 0, and that happens at pi over 2 plus pi n. So tangent of x is continuous when x does not equal pi over 2 plus pi n, where n is an integer. Okay. So this is continuous. Tangent of x is continuous when x does not equal pi over 2 plus pi n, where n is an integer. Next, g of x is equal to sine of 1 over x when x doesn't equal 0, and 0 when x does equal 0. So the limit as x is approaching 0 from the left and the right, well, it's happening at 0. If you look at the graph of this, this is an oscillating function. So it's behaving, or it has oscillating behavior. And so I can't plug that hole. It's not a removable discontinuity. So it is discontinuous at 0, regardless if I have a value there or not. So this function is going to be continuous on -infinity to 0, and then 0 to infinity. So that's part B. Part C. Right here I have that oscillating behavior again, but that oscillating behavior is being multiplied by 0. And so when I multiply anything, even oscillating behavior, by 0, it's going towards 0. And so this can be plugged with this 0. And this is continuous on all real numbers, or -infinity to infinity. And the last one, the intermediate value theorem is a proof of existence. You don't need to find the 0. You just need to show that it indeed has a 0. And with the intermediate value theorem, if I have an A that has a negative and a B that has a positive, or vice versa, it's enough to show by the intermediate value theorem that there is a 0 on our function. So what I'm going to do is find f of 0. F of 0 is equal to 0 cubed plus 2 times 0 minus 1, which is equal to negative 1. And then I'm going to find f of 1, which is 1 cubed plus 2 times 1 minus 1. It's 1 plus 2 minus 1, or 2. Okay, so now I have a negative. F of 0 is negative. F of 1 is positive. Therefore, by the intermediate value theorem, there has to be a 0 between 0 and 1.